Hi, this is Chris Armstrong from Regal Technologies. Let's talk today about an introduction to radio frequency signals. We're going to go through a couple different examples of how we use RF signals in our lab and look at it from a perspective of a few different instruments. Today we're going to use an oscilloscope, a spectrum analyzer, and a waveform generator to generate our signals and look at them, visualize them in different ways. Let's get started. First thing we're going to learn in this lab session is how to view basic RF signals in both the time and the frequency domain. We're going to talk about how we look at amplitude differently in those two domains, whether it be more power like a spectrum analyzer or in voltage space on your oscilloscope. We're going to define and look at examples of some basic modulation schemes, including amplitude, frequency, and phase. We're going to test out transmitting some analog data. We're going to transmit some digital data, and then we're going to talk briefly about some more complex digital modulation schemes used in Wi-Fi and Bluetooth and other transmissions today. First, in these examples, we're going to be using a couple different pieces of Regal equipment. The DG1022Z waveform generator, the DS1054Z oscilloscope, and the DSA705 spectrum analyzer. We also have some cables and connectors we're going to use, including an audio jack to BNC cable, other BNC cables, and a BNCT, and some converters we'll be using throughout this presentation. This package comes with setup files for these instruments, as well as a couple other models of spectrum analyzers you might be using in your Regal lab. So here's a preview of how we've set up our instruments to start. We've loaded the start setup files for each, the generator, analyzer, and oscilloscope. And we've connected the output of the channel 1 of the generator to both the scope channel 1 input and the RF input on the spectrum analyzer. We're going to use this basic configuration to show both of our signal both in the time domain and then in the frequency domain on the spectrum analyzer. So before we go to the instruments, let's look theoretically at what that looks like. This chart on the right shows you what we mean by time domain view and the frequency domain view. So we have multiple signals combined into our primary signal that we're looking at. In the time domain, we see this over time with multiple sine waves on top of each other interacting. In the frequency domain, we see each frequency space as a separate bin or portion of our signal. So each view is ideal for looking at different types of modulations or signals. These two domains can be thought of as different views on the same three-dimensional chart or signal. Now let's go to the instruments and see what that looks like. So here's our most basic view of a signal in both the time domain and the frequency domain. We're generating a basic 10 megahertz sine wave. On the scope, we can see the sine wave, and this is 100 nanoseconds per division, so we can label the frequency at 10 megahertz. We can see that you get one sinusoidal wave every division on the screen. We can also see the amplitude here expressed in voltage, either volts peak to peak or in volts RMS. If we look at the spectrum analyzer, we see our 10 megahertz expressed as a single peak on the left side of the screen there at a power level in dBm. So the analyzer talks about this signal as a single peak in power, whereas the scope talks about this as an alternating signal over time in voltage. All right, so let's look closer at what we just saw in the instruments. Here's another view of the oscilloscope, looking at time, going from left to right on the screen. You can see the little blue circle shows we have 100 nanoseconds per division. So the blue line shows you that period. So the period of each wave is 100 nanoseconds, which makes the frequency of that wave 10 megahertz, which is circled in red at the bottom. On the vertical axis, you can see the voltage peak to peak circled in orange, and that's really identified by the orange line, showing the plus and minus peaks of those waves. Now, if we switch to the frequency domain, now we can see on the spectrum analyzer a closer view. Here we're showing that peak identified at 10 megahertz, and it identified as a power at about minus 25 dBm. So on this spectrum analyzer, we're showing frequency from left to right on the screen. Lowest frequency being about being at 5 megahertz, going up to 55 megahertz. So how do we convert between voltage on the oscilloscope and power on the spectrum analyzer? Well, power, in this case, is measured in dBm, which follows the equation here. On this spectrum analyzer, like most, we use a 50 ohm resistance. For any of these measurements, you can know a clean sine wave has a volt RMS equal to about 0.707 times the peak-to-peak voltage. That's the square root of 50. dBm is always relative to a milliwatt. So 0 dBm equals a milliwatt, and it goes up logarithmically from there and down. So 30 dBm is equal to 1 watt of power. Our signal here is equal to about minus 25 dBm, or about 11 millivolts RMS. In these ranges, the spectrum analyzer is much more precise than the scope. So if we want to measure power, we should look to the spectrum analyzer for the most accurate readings. So now that we understand how we convert amplitude and voltage into power, let's look at our next demonstration, which is really about amplitude modulation. Here I've set the AM modulation files up, setup files for the generator, analyzer, and oscilloscope. We can see here on the oscilloscope how this amplitude modulation file, see the signal is often at the full amplitude, but sometimes comes in smaller. Right? So as the amplitude changes, you're getting multiple wave fronts shown on the instrument. That's how it appears in the time domain. On the spectrum analyzer, we can see that same modulation occurring, and what happens is every time the analyzer sweeps, it captures a different power level at that frequency. And you can see it moving up and down as it's getting more or less power. Here you can also see it dramatically changing from a relatively high, minus 25 dBm, all the way really down to the noise floor. So this is an amplitude modulated signal where the power or the voltage, the amplitude, is being modulated over time. So this slide shows us the close-up of those two instruments together, with the spectrum analyzer modulating up and down, and the oscilloscope showing you the full depth of that AM modulation. AM modulation, amplitude modulation, is really the most basic type, much like an AM radio station. Varies the power of amplitude over time, in this case really sending analog data. Let's take a look at a different type of modulation, frequency modulation. Now I've set up the three instruments using the FM modulation setup files. Then I activated the output on the generator, and this is what we see. So on the scope, this is an interesting example of how you see the frequency is changing. That is, the time between peaks is changing. Because we're triggering in the center, that point is solid. If we move that trigger point to the left of the screen, now we can see as you move it over in waves, you get more and more discrepancy as the frequency is changing from shorter frequencies to longer frequencies. We see the same thing illustrated on the spectrum analyzer on the left. Here we can see how the frequency is quickly moving, about half the screen width, from about 8 megahertz to 10 megahertz. Actually 8 to 12 megahertz, centered around that 10 megahertz in the middle. So that's giving you that frequency shape that's shifting quickly, modulating between different levels, and that's how you can encode analog data, just like a FM radio station, selecting different frequencies for different data bins in each area. So that's an FM modulation. This slide shows what we just looked at in that demonstration. You see the scope on the left, the spectrum analyzer on the right. Again, the scope showing the voltage over time, changing the frequency, the pattern, the width of each sine wave. And on the right, you see the spectrum analyzer with a band of power between 8 and 12 megahertz from left to right on the screen, where we have power being emitted and really scanning through each sweep of the analyzer. Now let's look at a third way we can modulate basic signals, and that's phase modulation. Let's go back to the instruments. So now on our three instruments, I've set up the phase setup files, which now give us a phase modulation. And actually this is a special type of phase modulation, really a 180-degree phase shift key. This means that the phase is going to change at single points between 0 and 180 degrees And that gives us a nice, easy way to look at it on the scope to see the difference. And here on the scope, we can see we're now triggering on the change in that phase using a pulse trigger mode. And now you can see that on the left side of the screen, the sine phase is normal. But then, right as it switches in the center, you can see it's offset by 1 division of where it otherwise would be. So it's inverted or 100 degrees out of phase. So that is a single transition going back and forth of 180 degrees in phase. Now let's look at the spectrum analyzer. The spectrum analyzer doesn't see anything about phase, right? So it just knows the frequency at the center, which is at 10 megahertz. But what's interesting is that in a phase modulation like this, due to the speed of the phase modulation, at the speed of those transitions, you're getting artifacts at other nearby frequencies especially. And that's what those tails are to the left and the right of the spectrum analyzer. You can see power in adjacent frequencies caused by the quick 180 degree phase adjustments. So as we look further at these modulations, we'll start to understand how these changes in power and how a modulation emits power across a wider part of spectrum is really key to the usefulness and functionality of all the types of modulation that we talk about. So a closer look at what we just saw. Here on the left, you can clearly see how the phase is changing by 180 degrees right in the center of the oscilloscope. You can tell because on the left side of the screen, if you count from the left, the odd divisions is where the sine wave is high, and the even divisions are where it's low. And then when you cross the center, you see the second, fourth, and sixth from the center. We've now switched to where the even divisions are on the high side and the lows are on the odds. So that's a 180 degree phase shift right there in the center of the screen. And on the right, you can see all those harmonics on the spectrum analyzer going out to the nearby frequencies, really caused by the rapid adjustment of phase right in the center. And it's easy to kind of see how that pulse in the center of the scope that's really only a part of a sine wave really does have other harmonics in it, really higher and lower frequencies nearby in the spectrum. Now next, let's go ahead and talk about how we can move this to actually transmitting data. So the next couple experiments we're going to talk about first in the slides and then go to the experiments themselves. Transmitting both AM and FM data is a little more complicated, but we can set it up to do the same thing. Here we're going to use the external input for modulation on the back of the DG1Z, and we're going to use this audio source, really just like a phone, to put music into that AM and FM encoding. And then we're going to use the demodulation capabilities of the spectrum analyzer to pull that audio back after we've transmitted it encoded either in a cable or with a pair of antennas. And then we're going to do the same thing with the FM as well. So now let's go ahead and take a look at some of the implications of this and an actual setup experiment using analog data transmission. So here we've adjusted the configuration only to add an external modulation source in the back of the DG1Z. There we're using my phone just to play a little classical music for us while we demodulate it. So here you can see the generator is modulating that signal, putting it up on the 10 megahertz carrier, and then transmitting it really in this case both to the scope and the spectrum analyzer so we can visualize it. Then the spectrum analyzer is doing the additional work of demodulating the signal into the speaker here where we can hear our music come across. The interesting thing here is we can see in real time, you can see the amplitude modulating slightly on the scope, but really very difficult to fully demodulate it in that sort of time domain view. The spectrum analyzer is set up to do 10-second chunks, so the display doesn't change, but the audio comes out continuously 10 seconds at a time. So that's how we really set up a basic analog modulation scheme to modulate the amplitude, bring it across the spectrum analyzer, and demodulate it. So now I've changed the setups to load the FM external setup files. So now we're loading the same audio, externally modulated, this time as frequency. On the scope, I've moved the trigger over to the left side, so we can see how the frequency changes over time. So you can see the more alterations as you get about 5 or 10 cycles, you can start to see the modulations. But again, the spectrum analyzer can pick those up more clearly. So it's able to immediately, in its demod mode, demodulate that FM right back into the audio source that's generating it. And here we switch our signal gain and our volume settings to optimize that. But again, a great reason why FM works really great for this sort of application is because whether you have cables connected like this or antennas, the frequency changes are easy to pick up. Whereas with amplitude, obstructions, range, buildings, things like that can cause the amplitude to fluctuate, whereas the frequency tends to be more steady. So there's a great example of a simple FM external modulation into our spectrum analyzer using audio. So in the last example, we were transmitting and demodulating analog data. Here, let's look at a similar modulation, but with digital data. So this is an amplitude shift key, which is in essence an amplitude modulation where there are only two values, a high amplitude and a low amplitude, that are equivalent to a 0 and a 1. And now we've taken a slightly different connection scheme, and we've hooked up the demodulation audio port coming out of the DSA 710 and have it going into channel 2 on the scope, so we can see the bit pattern, in essence the ones and the zeros. So here we have, in the yellow on the top, the carrier, the amplitude modulation. We can see the spans of 500 microseconds each, where it's high and low. And then in the blue, we can see the demodulated zeros and ones coming out of the analyzer that are coordinated perfectly in time. If we looked closely at the spectrum analyzer, we can see the amplitude changes, the amplitude modulation changes here as they go from periods of high and low within a single sweep. So that creates a little bit of spectral energy, but really is a great way to see both the time and frequency domain view of an amplitude modulated digital signal, in this case an amplitude shift key. Here's our second example of digital data transmission and demodulation. Here we're looking at an FSK. So we've loaded the FSK settings for all three instruments as a frequency shift key. So the signal is moving between two frequencies. In this case, like with most frequency modulations, we're moving between two frequencies that are relatively close together. That's causing a couple things. First of all, on the scope, we can clearly see the demodulated bits coming from, in the blue, from the spectrum analyzer. We can also see that the channel 1, the yellow, is very consistent. It's at a much higher frequency. And I can actually go ahead and switch over to trigger channel 1 if we want to see it directly. So those are those frequencies directly. We can see how it's changing beneath. But really, there's no settings on the scope where we can easily see the change in frequency because the two frequencies are just too close together. However, the spectrum analyzer is picking it up nice and easily because it's able to completely demodulate that signal, which we can see in the bits here as we move out to the 500 microseconds. So at a 1 kilohertz frequency, that input is changing, that bit is changing, and the spectrum analyzer cleanly can pick out the highs and the lows, even though those frequencies are close together. And that's one of the advantages of the frequency domain, is the ability to easily separate nearby frequencies together using the RBW settings and the demodulation settings on the spectrum analyzer. So let's summarize that digital data transmission that we just looked at. So we use two types of modulation, an amplitude shift key and a frequency shift key. In these modulations, there were just two levels. In one case, two levels of amplitude or two frequencies. One is demodulated as a binary 0, the other a binary 1. We connected the DSA demod jack, and then we could see both the signal and the demodulated ones and zeros together on the oscilloscope. Here's a picture of the oscilloscope with the amplitude shift key modulation, where you can clearly see the two amplitudes on the scope screen on the yellow, and you can see the bit values in the blue. On the spectrum analyzer, you can see how the amplitude was changing in 500 microsecond increments on the screen. Here, we see the frequency shift key, where now on the oscilloscope you really can't see the difference in frequency because the two frequencies, in this case 9.9 and 10 megahertz, are just too close together to easily identify. However, the spectrum analyzer, as you can see, is easily able to demodulate it and separate those two values to give you a clean demodulation. There are also more advanced forms of modulation that we want to talk about. And really one key advantage to these as you get more complicated is that they tend to use spectrum much more efficiently. This is because spectrum has a high cost and you really interfere with other signals within a piece of spectrum that is either leased or is available in an ISM band. And those bands really need to share that spectrum. So signals, putting more and more data throughput in a particular piece of spectrum with a certain amount of power is sort of one of the keys to developing more efficient means of data transmission. So much like our FSK signal that stayed in a narrow frequency range, these modulations are optimized to use a number of these signals together in channels, much like FM radio stations. This is called frequency division multiplexing, where you have a frequency bin or a frequency channel associated with a particular signal, and then you divide up a spectrum into pieces or channels. There are other ways to do multiplexing with more advanced signals, and we'll look at a couple here, including time and phase. One good example is what we use today for Wi-Fi signals very commonly, a complex signal type called QAM, or quadrature amplitude modulation. This really uses a combination of phase modulation and amplitude modulation together with two sine waves that are at the same frequency but 90 degrees out of phase. In this sort of a data type, we call these signals I and Q. So this is a type of IQ modulation. Each of these two waves is modulated with both amplitude shift key and phase shift key modulation. So a basic type of this, like QAM16, demodulates with 16 possible values based on the phase and the amplitude of each of the two carriers. One way we would commonly describe this is with a constellation diagram at the right, which shows each value for amplitude and phase for each of the signals, and how you can demodulate that into a set of symbols, or in this case, 4 bits. Now, more advanced instrumentation can do this demodulation directly, such as our RSA 5000 has a toolkit for showing the constellation diagram and the bits and the symbols for each of these types of complicated modulations like QAM. So many of these RF transmission strategies, though, are derived from really the basic principles that we've already talked about, as well as some of your common engineering challenges, including decreasing power to save battery life, improving signal-to-noise ratio, reducing errors, and then just being more efficient with that bandwidth, improving your density for your signals. Let's do one more experiment where we can look at the relationship between two signals in phase. We can do this using XY mode on a scope. So we're going to look at a few amplitude shift key and phase shift key using the XY mode on your oscilloscope. Here we've set up XY mode on the scope to look at two channels that are both ASK, or amplitude shift key modulated. So we've set up those setup files, we've turned on both outputs, and now in this mode, to finalize this setup, you need to adjust the start phase by going to the sine menu, start phase on channel 1, and here we can adjust the start menu. The phase will not align directly because both channels are amplitude modulated, so you have to change the start phase until you get a nice round figure on the scope. And so let's look at about what this represents. So at the top we can see the time domain, and we can see that these two signals, we can zoom in a little bit, we can see these two signals are 90 degrees out of phase. The yellow channel 1 being 90 degrees before the blue. And we can tell that because of the circular nature of the XY curve. That shows you that you're one way or the other, either 90 degrees out of phase between the two channels. What's also happening is you can see the two levels of amplitude here. The inside circle being a lower amplitude, the outside circle being a higher amplitude. Another way to verify that these signals are 90 degrees out of phase is if we look down the center line of channel 1, we can see that when channel 1 is 0, channel 2 is always very high or low. When channel 2 is 0, channel 1 is high or low. So this really indicates you can see clearly it's 90 degrees out of phase, and we're able to look at the two amplitude rings as well. So this is different than a constellation diagram, but it is another way to visualize a phase difference using an oscilloscope in XY mode. So now we're looking at a phase shift key modulation. So we've use the USB stick to update to open our setup files on both the generator and the scope. We've turned our 2 output on. And now all we need to do is adjust the start phase on this channel here until we get really our full circle. So this indicates that we are, again, either 90 or 270 degrees out of phase between the 2 channels. That's how we know we've got these offset in the correct amount. So each of those makes a curve. And we can see at the top of the screen our 180 degree phase transition that we talked about before in channel 1 there, where it switches. And so you can see in the left half of the screen, the blue is leading by 90 degrees, and then it switches. And then on the second half of the screen, the yellow trace is leading by 90 degrees. But because we're always offset by 90 degrees, both of those symbol patterns results in a circle on our XY graph. So that's a great way to look at 2 signatures, 90 degrees out of phase. Here, the amplitude is stable on both channels, but the phase is shifting. But because it's only shifting by 180 degrees, and they're starting 90 degrees out of phase, they're always 90 degrees out of phase, resulting in that XY plot. So another way to visualize, in this case, phase shift key modulation using XY mode on our oscilloscope. So let's summarize that on this slide. Here, we demonstrated our 2 types, ASK and PSK modulation, using 2 signals coming out of our generator going into channels 1 and channel 2 of the scope. And we can use XY mode on the scope to visualize these in a different way. Because we wanted both channels to be 90 degrees out of phase, we in essence create circles on both the ASK and the PSK. On the ASK, we can see the smaller circle for the lower amplitude and the larger circle for the higher amplitude signals. On the PSK, we can zoom in there and see how channel 1 is leading for half of the trace, and then channel 2 is leading for the other half of the trace. And that switching is the 180 degree phase shift occurring on channel 1 in this case. So those are great ways to use the XY mode to visualize how signals that are out of phase can be used to both transmit data at the same time and what their relationship really is in the time domain. So let's summarize. RF signals transmit data by changing characteristics of the signal, things like frequency, amplitude, and phase over time. They can be combined into a lot of complex and more efficient modulation schemes, and researchers are coming up with new schemes all the time to make data transmission denser and work better on more efficient pieces of spectrum. Analog modulations transmit complex signals like audio, whereas typically we use digital modulations to work with data. So really any computer or electronic system, whether it be Wi-Fi, Bluetooth, cellular, are all really transmitting digital data. So being able to think about these signals in both the frequency domain and the time domain is a great way for engineers to provide value and really insight into their design and their systems when linking RF signals with regular electronic design.